Hey, good evening, everyone. Celso Batalha Soten, and yesterday I was going to initiate today's talk, showing an animation of plate tectonics at FET, Colorado. For some reason, I cannot run in my computer. I think I have a problem with Flash, um, but let me show you. Just a second, let me stop communications. Yeah. So this is my screen, and what you do, you go to, you might be able to run in our computer. Do a search in PHET Colorado, PHET Colorado, University of Colorado Boulder, and then play with simulations, and then you go to Earth Sciences, because plate tectonics is a part of Earth Sciences, and then there you go, plate tectonics. You click on it. And since they updated, oh, Windows only, that's why I can't run in my computer. My computer is an Apple machine. Okay, so if you have a Windows, you might be able to run. So I cannot. In fact, I don't know if that is the same with all animations. Well, for instance, this animation I can run in my computer. But it's interesting and very well done, because especially if you have kids that are learning mountains formations and how volcanoes are formed and how oceans are formed, how valleys are formed, and how all the major landscapes that we find on Earth, they are the result of plate tectonics. So the idea is our planet Earth is divided in 12 or more major plates. So think about the skin of our planet, the lithosphere is broken in plates, and these plates have relative motions. Some of these plates move against one another, and some of these plates move apart from one another. Some of these plates pass one another. So this is called transform fault. This is called the boundary, so this boundary is has three main types of boundary. So one is the transform fault, as I mentioned, collisional plates and divergent plates. So when they move apart, and this animation allows you to create plates of different densities. So a plate that is lighter, that has pretty much can be found in the continent area, and is where the sediments that we are on happen to be on top of granitic type of rocks. They are relatively lighter than the rocks that happen to be covering the ocean floor. So the rocks covering ocean floor are thinner and denser. So as a result, when collision takes place between continental and oceanic plates, there is a phenomenon called subduction, in which the heavier oceanic plate slides under the lighter continental plate, and as this thicker, not thicker, but thinner, but denser plate moves inward, it brings with it sediments and water, because it's in the ocean, and this helps to reduce the boiling point of rocks in that region, pretty much inside the Earth interior. And by reducing the boiling point, it melts, right? The rock melts. And as it melts, it bubbles up. And then you have formation of volcanoes and all of that. So you can see this animation and the simulation quite well in PHET Colorado. So please make use of it. Before I go over the slides, which I started yesterday, I start posting comments on the discussions, this week discussions, which was based on star formation. And I would like you to write some statements indicating your understanding of star formation using core materials, or better saying, key phrases or elements that are part of star formation. So I wanted them to include in your narrative those elements, and they are giant molecular clouds. You should include protostar, you should include the pre-main sequence, should include fusion reactions, you should include, there are several terms. And I started correcting yesterday. The discussion is much better than the astrological one. You guys produce better information, and I'm correcting as I read. So Friday, I will go to another batch of reading. So if I already post on your comments, you can improve the elements of your test so that on Friday or Saturday, I can read it again and put more comments in there and improve your grade. That's the whole point. Okay, so the discussion is open, is about star formation, and which is one of the fascinating topics of this course. Without technical information on the subject, we don't think that the stars are in fact formed. They have a beginning, they have a development, and they end their life cycle as anything else in the universe. The universe is a universe of transient elements, and big stars or galaxies are just one of them. Darwin was the one who said the individual, we are not fixed species. We are always in transition, and this can also be applied to stars, although stars are not biological beings, but they are formed. And now you should know, out of gas and dust. So out of a giant molecular clouds, and gravity and rotation and angular momentum are important ingredients in the formation of a star. Within the giant molecular clouds, in certain locations, the densities should be good enough to allow gravity to initiate the contraction. And once gravity initiates contraction, now nothing can stop for millions of years. So gravity would just bring the gas to a center of mass. And in that center of mass, and it's pretty much illustrated in a sequence of figures in our chapter 5, you ended up with a central core with a protostar surrounded by a circumstellar disk, and more gas that happened to be overlying this core system falls onto the equatorial plane, forming a major circumstellar disk that later on become a circumplanetary disk, out of which planets and satellites and asteroids, comets, and everything else ended up being formed. Now, in chapter 6, we focus on terrestrial objects. Those they have a solid surface, and as a result, impact leave marks, and these marks are called craters. So if you look at pictures of the moon, let's see if we can get that. So you can find a whole range of features, and these features are craters or the result of impact. Craters are circular, and if they appear to be elliptical, like in this figure here, is because we are looking at an angle. And what is circular, looking at an angle, appears to be elliptical, as it is here. But craters are all circular, and the reason for that is when the impactor, which is whatever rocky material or ice material like a comet or a piece of comet that hit the surface, when that happens, the amount of energy that the impactor carry is so magnificent that lots of that energy is converted into shock waves, and the shock waves are responsible for carving the basins, for carving these craters that we are seeing in these pictures. And so if you want a rough estimate of the ratio between the size of the crater and the size of the impactor, the size of the rock that hits and formed the crater itself, is probably a ratio of 10 to 1 or 10 to 2, which means the impactor is 1/10 of the size of the crater itself. So most of it's different from when we throw a rock in a sand box. So we throw a rock in a sandbox, and the size of the crater formed is about the size of the rock we throw. So unless you put a lot of energy in the impact, you might create, some crater that is a little bit larger, a couple of times larger. But to make it so big is require some different sort of energy being dissipated, and that is pretty much shock waves. You can see the features are such that the craters have rims, these circular rims on the top of it. Some of these rims are sharp, indicating the youth of this crater. Some rims are kind of fuzzy and not well defined, as you can see over here. And that is why, and I hope you can see all of that. Supposedly I'm taping all of this. So if you don't see what I'm showing, is because something's wrong. But supposedly I'm sharing my entire screen, so whatever appears here, you're supposed to be seeing. That's at least is my understanding. If it's not, let me know, and then I will try to fix it somehow. But in this major crater here, the rim, in fact, is all kind of eroded because it's an old crater. In addition to this sort of indication of the old age of this landscape, you can also see the crater itself is filled with basaltic flow. And this basaltic flow hardened, and then more craters and more impact happen on that hardened basaltic floor, and then you have these landscapes. So you can study how young a impact is with respect to others by using elements from geology. Cross-correlation stratigraphic techniques in geology can allow you to determine which craters is old and which craters is young. For instance, if you look at this little tiny crater here that happened to be on top of the big ring, you can see that this tiny little crater is younger than the old crater because it's falling on top, right? Same thing with this crater here. This crater is younger than this crater, but those two on the top are even younger than it because they happen to be on the top. So I would say this is younger than this, which is younger than this, which is younger than this. And you have to do further analysis to compare the youth of this crater with the youth of that crater. So you can do these correlations to figure things out. But also in the moon surface, you have central peak, which indicates the youth. The central peak is not eroded. You can see riles, these kind of canyons you can see indicated here. And they can either be formed by lava tubes that collapsed when this basin was being filled by lava, can also be the result of cooling of the entire basin, and then that leads to cracks. You can see these features here that could be associated with part of the flow. You can see the ejecta blanket around this crater. So all these different features can be studied. And since they are so archaic, 3.8 to 4.2 billion years of age, these can only survive in a place that has no atmosphere, like the moon, and in a place that has very mild erosional agents. So one of the main uh, events that lead to erosional effects on these craters is when impacts raises up dust, regolith, called regolith, and some of the thinner dust takes some time to settle down. And when they settle down, they erase these sharp edges. And then you see the feature that older the crater is, the less well-defined the crater itself is. Now, Mercury also shows similar features, right? So you can there is always some crazy thing when we go Google. And of course, there are no snakes in the moon, right? There are nothing of that. And certainly this is not on the moon. Okay. So, and your book gives nice understanding of all these different things. And this graphic here indicates how the rate in which impacts take place on the moon and in the solar system in the regions closer to the sun have fallen down as the solar system itself evolved. So from 4 to about the age of moon's formation, the percentage of impacts have fallen dramatically. So if you think about planet Earth, so planet Earth also, when it was formed, it was subjected to major bombardment, we call bombardment. So lots of rocks fell on it. So lots of craters were formed here. But Earth has two major features that are responsible for erasing all these major features over the years. And one is plate tectonics. So when subduction takes place and heavier plates slide under the lighter plates, so all the craters, all the features kind of go away and you lose them. So in few million years, you might erase several, you might have erased several indicators of craters that exist on our planet's surface. That's one of the reasons. So there are very few areas on Earth, and they are called shield regions. Shield regions. They are made of a very archaic type of topology, and the geology indicates rocks that are about 4 billion years of age, and that region never had gone in a process of subduction. It's just a lucky point. So you can buy a house there, and the house is going to be standing for several millions of years. But if you buy a house, let's say in Los Angeles or in California, San Francisco, in a few million years, it's going to be in the Alaska Trench in Alaska, just going underground. So be careful. Weather-wise. But Earth has a second feature, and the second feature is hydrological cycle. So the hydrological cycle on Earth, which is responsible for bringing rains and snows and all of that. Now, if you go visit the Sierras, you can see the rivers are so beautiful. They are bringing so much volumes of water from the Sierras, from the top snow, because it's melting now. And these rivers are heavy because we got, luckily, we got good snowpack, and this is good for California after years in the drought. But this water doesn't come down without some consequences. So the authorities are considering what to do to preserve the levees, and so that these rivers preventing overflow and preventing damage, and because they are very important erosional agents. Rivers are important erosional agents, as well as winds and as well as glaciers that also move and carry material. So all of these erosional agents, which are we study in geology, they are responsible for taking sediments from one place and take to another. And as they do that, they reshape Earth's surface. So what looks like, some monotonous landscape today probably in 100 years, it's still going to be the same, but unless there is some catastrophe. But if you give enough years, 1,000 years, 2,000 years, they will slowly change. Mount Diablo is raising up as a result of thrust pressure that is provided by Calavera's motion, but also is being eroded because of rain. So when you calculate the net, there is an effect in Mount Diablo, which is, oh, it's raising up every year a little bit. So Earth changes its landscape all the time. We can measure the rocks using radiometric dating, and the system is very robust as long as you have a sample of rocks that are considered pure and you don't have a mixing. If you do have mixing, you have to use different samples to measure different decay. Now, earthquakes. Earth has earthquakes, and earthquakes are a direct product of plate tectonics. When plates move, for instance, if you have a transform fault and the two plates are moving, passing one another, in certain regions, friction, or if you want to use the word viscosity, but friction will be such that it's going to put a halt to the motion. So that halt will build stress, right? So the plate keep on moving. So the energy that moves the plates, fantastic energy, is there, but is now being halted by a opposing friction force that eventually is released. So when this energy is released, recall that an earthquake, and this energy is released in the form of waves, and they are called seismic waves. So there are three major types of seismic waves we study in the book, and they are P waves, compressional waves, S waves, shear waves that have motion that is transversal type of motion, in which the energy moves in one direction, but the material that is being serving as a medium for the wave move in a direction that is perpendicular to that of the wave propagation. And there is a third one called surface waves that move on Earth's surface. Of course, that is the most damaging one. But it was interesting about the P waves, the compressional waves, and the transverse waves, S waves, is that P waves can move either through solid material or liquid material, but not the S waves, not the transverse waves. The transverse wave, they rebound, they reflect off liquid surface. And by knowing that, geologists were able to identify on Earth interior the existence of a core that is liquid, is a liquid core. And then you think, how do we know there is a liquid core of iron on iron and nickel as an alloy in our Earth interior? Have we gone there? Probably not. I mean, the deepest part of Earth that we had gone so far is 12 kilometers or so. It's not so much. So, and this interior, we are talking about thousands of 3,000 kilometers or so inside Earth interior. So we haven't gone there. So how do we know? That's the question. And that's the question we ask you and we ask in chapter 4. How do we know about Proxima Centauri? How do we know about quasars? There are hundreds of millions or sometimes billions of light years away from us. How do we know about them? How can we talk about them if we haven't been there, right? We haven't visited them. We haven't brought any piece of these materials to our lab. Guess what? We know because we know how energy behaves, basically. You go to your dentist, and your dentist, the first thing she does is take an x-rays, right? So why it takes an x-rays? So she doesn't go there and start breaking up your teeth to see if you have some infiltration, some leaking going on there. So we take an x-rays because x-rays allows for them trained dentists to have some idea of what is inside your tooth without cracking open, right? So that's great. By the same token, geologists know about Earth interior, not because they cracked open Earth or they built a major, tunnel down to Earth interior. Far from that. So they use earthquakes, natural waves, but also atomic and hydrogen bombs and the waves that were generated by these explosions to make a 3D map of our planet. And that's how we know how our planet is in its interior without going there. Again, this is one of the beauties of science, is that science is not an attempt to tell the truth. Like this type of narrative exists a lot in religion. Oh, we tell the truth. We are the truth. I mean, science is not like that. Science is, okay, based on the laws of nature that I have studied, that I know they exist. So if I'm holding a pen and if I let it go, there is a law that says there is a gravity force that will bring the pen down. And no matter how many times I do this experiment, right, I can get, close to retirement in several years, and the pen is still going to fall. So there is an underlying law taking care of this process. So what scientists do, they identify all these basic laws. They repeat and they create a phenomena that you can predict what they're going to do. And then you explain this law. You create mathematical laws to explain them with the empirical laws. And then you create a theory based on the laws of nature you have identified and you have proven to explain correctly phenomena. And once you create a theory like plate tectonics, you can make prediction. Like plate tectonics based on statistics, you can say, well, Hayward fault has been going on every 200 and so years. I don't remember exactly the number. But so if you go past in the history of Hayward fault, you can see that every 200 and so years, and my number might not be right, but certain amount of years that is always fixed, there is a major earthquake, magnitude 6 or 7, in the Hayward as a result of San Andreas that is moving all the time. And when this happens, you have major catastrophic event. So geologists use this fact, this repeatable phenomena, to make a prediction. The prediction is, it's going to happen. It's going to happen again. And it could be now, it could be plus or minus 10 years or 15 years, but it's going to happen. Magnitude 6 or so in Hayward is going to go. That's one example of how science works, using statistics in the case of earthquakes. But when I'm pretty sure you're finding several examples on how science basically works. And now in star formation, especially in the realm of exoplanets, you might be learning a lot of those phenomena. Right now, people working on exoplanets are preparing and trying to make predictions on what they will observe once they are able to use this James Webb telescope to identify molecules that might be footprints of life in this exoplanet. So they are working hard to make sure that once the telescope is available and once they start collecting data, they can use that data to quickly identify their predictions. And if the predictions are met by data, then that's great. So it seems to be some in a good direction. If it doesn't, why is that? That's how science works. We are not sitting down on a mountain saying, we have the truth. We say, hey, based on what we know, based on how we explain everything else in a consistent way, that is the best explanation we have to this fact. And if you have a better one, I'm happy to sit down and listen about it. So terrestrial planets and terrestrial objects are those, and in tomorrow, in fact, yes, tomorrow I will post a quick, oh, by the way, tomorrow we have observatory at night, is our public viewing, and I will send an invitation to you all. If you want to just go get by and see Jupiter and Saturn, just feel free to. It's going to be a good night. Bring your date, bring your companion, bring well-behaved animals, and let's get some good time in there. And perhaps a chance for you to see the telescopes we have and maybe get you excited to enroll in one of our astronomy lab classes in the fall. All right? Okay, good night to you all.